I welcome you again for this NPTEL course on earthquake resistant design of foundations, and today is the fourth lecture in this course. As you are aware that the course has been divided in 5 modules, and then second module we have already talked about the general requirements, and then we also discussed the bearing capacity in the second. Today this is in the fourth lecture, we are going to talk about the bearing capacity and settlements which is related on the shallow foundations. Now, talking about the this is the part of the chapter 2, and that is chapter 2b basically, and what you have the total settlement of shallow foundations. So, and then we are going to talk about settlement of foundations on granular soil, continue with that modes of types of settlement, and finally limiting angular displacement will be also covered. So, continue with that, let us first talk about total settlement of shallow foundations, and when we have total settlement of shallow foundations, you could see that total settlement in general is given by the relation of immediate settlement, then you have the primary consolidation and the secondary compression. So, this consists of 3 components as written in the slide, where SI is immediate settlement or elastic settlement, which normally takes place immediately, that is normally within 7 days after the construction. Then the primary consolidated settlements, which is due to the gradual expulsion of pore water from the voids of soil, which results in dissipation of excess pore water pressure, and as a result in increase in effective stress. So, this is also based on Tarjagi's theory of consolidation. And secondary compression, which is mostly for the organic soils, occurs at constant effective stress. Now, the issue is this one, that what is the rate of the settlements for this. So, if you see this chart here, then you could see that settlement versus time is given. So, the first part, which is immediate settlement, is not time dependent, and while the second part, which is called the primary consolidation and secondary compression, they depends on the time. That means, as the time passes, the settlement increases, and there is a time factor which is called T100, which is basically time required when excess pore water pressure is 0. That means, whole of the pore water pressure get dissipated. So, this is basically the settlement versus time chart for the shallow foundations. Continue with that. Now, the issue is this, which of the 3 components is more important. So, the answer is not simple, rather it depends on the type of soil. When you do have the granular soils, the immediate settlements accounts virtually for the entire settlement, but when we talk about inorganic clays, it is primary consolidation which accounts for most of the settlement, while for organic soils secondary compression accounts virtually for most of the settlement. So, depending on the type of soil, this which component will dominate will depends on the type of soil. So, when granular soils, it is elastic settlement or immediate settlement. Now, continue with that. When we say immediate settlement, that is for the important for granular soils, this can be worked out using the equation written here, which is you can see that Q into B, where Q is the surcharge coming load from the top, and B is the width of the footing, while mu is the Poisson's ratio and E is Young's modulus. Then IF is an influence factor for settlement, which depends on the shape and rigidity of the foundation. So, we can work out the immediate settlement using this empirical relation. However, primary consolidation and secondary compression is not easy to calculate like such an equation, rather we need to conduct take the measurement, and then only one can ascertain the value of settlements. Continue with that. When we say there is one issue is related to contact pressure. So, when we talk about contact pressure, it is can be different for different types of, if you have the footing is flexible, in that case contact pressure at the interface of the footing and the soil is uniform, and and this happens with the respect of the type of subgrade under the soil material. That means, whether you have the clay or you have the sand, the the pressure distribution is uniform for flexible footing. However, when you do have the rigid footing, which is shown here, in that case the shape of the contact pressure will depends on the type of subgrade material. So, you could see in this first case, when you do have clay, in that case the pressure is more at the end, at the corners, and minimum at the center. But if you have the cohesionless sand, then in that case it is other way, that means pressure is more at the center and minimum at the edges. But if you have the C5 soil, where you have intermediate, means you have cohesion as well as the angle of internal friction, then it is more or less uniform, as shown in this next figure. So, the contact pressure is important, and thus this contact pressure variation governs the settlement. Continue with the settlement, then we have already talked about total settlements of shallow foundations. Now, let us talk about settlement of foundations on granular soils, which is important and easy to as we just discussed, that for granular soils it is the elastic settlement which is most important. Then continue with that, how to find the for the granular soils. When we talk about cohesive soils, you know that the compressibility and consolidation parameters are important, and they can be determined from the laboratory test. The reason being, because you can collect the what we call undisturbed samples, which can be tested in the laboratory. However, when you have granular soils or cohesionless soils, then it is difficult to get undisturbed samples. As a result, it is recommended that for the granular soils, the field test or institute test are preferred, and for the field test, and they are more reliable than the lab test. So, for the settlement to find the granular soils, the most of the time two types of tests are used. One is plate load test, which is very popular, and another is penetration test. Penetration test could be conducted either using SPT, which is a standard penetration test, or CPT, that is cone penetration test. Let us discuss these tests in the next slides, that what is how the plate load test, and then that how to find the settlement using SPT and CPT. When you have plate load test, the setup for the test is shown in this slide. So, you do what you have in this case, you have the girder which is anchored, and below the girder you have a proving ring, and proving ring is connected to a. So, what is important is here is the at the down, which is a plate of width BP. When you have what is BP, here BP is the width of the plate, and this plate is normally consist of mild steel, rough plate, and the width, this is a square plate. So, width could be anything, either it could be 30 centimeter, 45 centimeter, 60 centimeter or 75 centimeter. So, the width could be out of this range from 30 centimeter to 75 centimeter, any value, an increment of 15 centimeter can be selected. The width of the pit in which test is conducted is required to be 5 times the width of the plate, that means 5 times of BP, while the DF is called depth of footing. So, the plate is kept at the same level where later on the footing will be kept. So, depth is common, however, width is for the conducting the test, naturally the width of the pit required need to be more than the width of the plate, and the procedure is explained in the IS code, which is 188/1982, and the title of the code is method of load test on soils. So, all the details are given. Let us in brief discuss that so what is the salient features for this plate load test. As we already discussed, that is a square plate of mild steel is used. A small size is used for dense soil, while the large size is used for loose or soft soils. If the water table is above the level of pit, water is poured out to bring down the water table at the foundation level. So, it is important that water table should be like water need to be drained out, and water table need to be lowered. Load can be applied by using two mechanisms. One is what is called gravity load, another is called reaction load. and in these loads you have a sitting load of 70 kilogram force per centimeter square is applied, and once this load is applied, it is released after some time. Further load is applied in the increment of 1 by 5 of estimated load or up to failure, or at least when the settlement reaches to 25 mm. So, that means at least we need to have a settlement of 25 mm, or if already the failure load is estimated, then it is up to 1/5 of the failure load. Settlement is recorded at a time interval of initially for 1 minute, then 2.25 minute, 4, 6.25, 9, 16 and 25 minutes. These are all if you can find the root of these quantities. So, if you find then 1, 1.5, 2, these 2.5, 3, 4 and 5 will be the roots. And after 25 minutes the test is conducted at recorded, the data is recorded at each 1 hour. All the details are given in the code. Then what we do, the load settlement curve for the test plate is plotted from the test data, and the load settlement curve looks typically like this, which is shown in the next slide. This is the typical load settlement curve, and this is obtained from the, and these load settlement curves are you have the difference here. What you have, you could see that in this load settlement curve A, B, C, D 4 curves are there. On x axis you have the load intensity, which is nothing but the total load divided by the area of the plate, and you have the settlement. So, as the load intensity increases, the settlement is also increases, but there is no linear relation. So, if you see for A, where you have dense cohesionless soils, that means granular soils, there is a clear peak where you do have this load that increases, and once you have that you could see that if I highlight this part. So, you could see that there is a change, kind of a jerk, where from this point to completely changed. Then this was for the dense cohesionless soils, but for cohesive soils this is the curve B. So, they are totally different. For the same, that for the load this will go. So, the settlement is what you do have the settlement for the if I have the same load, and then for the same load the settlement is higher in this case compared to that for the settlement is higher for the A case compared to B case. Then we do have this is other way, the settlement is higher for the B case compared to the A case for the same intensity of the loading. However, the load carrying capacity is smaller for this clay compared to what you have for the sand. Then we have for the same settlement, if we check for the same settlement, the load carried by A is quite higher compared to B. Then C and D are the intermediate case. C is for the partially cohesive soils and D is the loose to medium cohesionless soils. So, these are the used for the there, but some empirical relations has been also used, and empirical relations are listed in the slide, and they has been given by the author Tarjagi and Peck in 1948, recommended that settlement of a footing on cohesionless, that means granular soils, can be found from this relation. In this relation, what is important to notice that there is a quantity 30 is coming, and this 30 number is in centimeter. So, as a result, this equation value of Bf and Bp, where Bf is the width of the foundation and Bp is the width of the plate, that also we need to be put in the centimeter. And once you put all the quantity in centimeter, you get a ratio of settlement of footing versus settlement of plate. That means, on the right hand side you get the ratio only. So, then whatever unit you choose for plate settlement of plate, then you get the answer in the same unit for the settlement of footing. So, basically if you know the dimension of plate, if you know the dimension of footing, and conducting the plate load test, what we do, we find the settlement of the plate and the corresponding settlement of the foundation can be found from this relation, which is valid for granular soils. The load settlement curve can also be used for finding the ultimate bearing capacity if you do not have the equation which is for using the bearing capacity factor. and here the ratio of ultimate bearing capacity of footing to ultimate bearing capacity of plate is same as the ratio of width of footing divided by width of the plate. So, this is given by this relation. These two relations like this relation and this relation, these are two are for granular soils. Now, these two are for clays. So, what you have here for cohesive soils, the settlement of foundation is directly proportional to the width of the footing. So, you have on the right hand side the ratio of width of footing versus width of the plate, and then you can find the settlement. For cohesive soils, again the ultimate bearing capacity is same as the ultimate bearing capacity of plate. So, there is no correction due to the width of the plate or width of the, so that is the case. However, this relation is not recommended for clays. So, it is not recommended that because as we discussed earlier, this plate load test is basically for the granular soils, and it will be better for the clays or cohesive soils to conduct the experiments in the lab rather than relying on the field tests. So, continue with this, and we have this plate load settlement curve. Then what is the, there are few limitations of plate load test which is listed here. In no case plate should be less than 30 centimeter width of should be there, that means minimum width of the plate should be 30 centimeter and maximum we discuss is 75 centimeter. The test is valid for the medium and dense sands. In case of loose sands, it underestimates the settlement. If soil is not homogeneous, effect of low bearing pressure shall be accounted. Actual settlement would be in that case higher than what you get from this test. And we need to understand that this plate load test is a short duration test. So, naturally this will be applicable to find the immediate settlement which is for the granular soils. So, the applicability of the plate load test is for more for granular soils rather than cohesive soils. Continue with that. Second way of calculating the settlement from the test is using penetration test. And when we talk about penetration test, you know that this SPT or standard penetration test is very widely used. And in this test using SPT you get the number n, number of blows. So, before we calculate the settlement using this number of blows, we need to apply two corrections. One correction is due to overburden pressure and another is due to dial tendency. The overburden correction factor, there are many empirical relations, but the relation is given here. N value here given is the measured value in the field, n prime is the corrected value and Cn is the correction factor, which is given by a relation 0.77 log 10 2000s sigma V naught. In this case, sigma V naught bar is effective overburden pressure which need to be put in kilopascal, that means kilonewton per meter square. So, we need to be careful while using this formula. It is 2000 is coming, in that case sigma V naught is here in kilopascal. And further there is a range for the value of Cn. It is recommended that the minimum value of Cn should be 0.4 and maximum is 2. If you see this equation, then you could see that Cn values are higher when the overburden is smaller, that means at the top, and the Cn values get decreases. So, the maximum value when you assume sigma V naught equal to 0, then this may give theoretically infinity, but that is not the case, or it may be higher than 2 values. So, if you see this chart where the value of Cn is given and sigma V naught, that is overburden pressure starting from 0 to 500 kilopascal is given. When you have at the ground level, your overburden pressure is almost 0, at that point the value of Cn is 2, while when you have at quite high depth. So, as the depth increases, overburden will increase. As a result, when the overburden increases, what you will have when the overburden will increase. So, as a result you could see that this is decreasing and it will continue to decrease when the overburden increases, but the minimum value is 0.4 and maximum value is 2. So, while using this formula we need to be careful that the like recommended value minimum 0.4 maximum 2 irrespective whatever you get from this formula. Once Cn is decided, then using this relation you can apply the correction for overburden. The second correction, which is for dilatancy, that need to be applied only for when the soil conditions are saturated and fines or silty sands is there. So, if you have the fines and sand inside the sand you have the fines and it is saturated, then only dilatancy correction need to be applied. And dilatancy correction, as you may be aware that this is when the value of n is more than 15, that only then it is required to be applied. Otherwise, when it is less than 15, n double prime is same as n prime, but if it is more than 15, then it will be 15 plus 50% of the larger values greater than the values which is greater than 15. So, for example, if you have 22, so 22 minus 15 it will be 7 that means 3.5 plus 15 18.5. So, using these relations you can apply the corrections. Once you get the corrected values, that means this the value of n double prime, then we can use the charts given by the code, and the code IS 8009, that is part 1 1976. This chart is giving this chart is for the gives you the value of n. In this chart, what you before this let us look on this chart before we use it. What you have on x axis width of the footing in meter, which is a normal scale, and it is going 0 to 6 meter, while on y axis you have settlements which is also in meter, but this value is per unit pressure, that means, and the pressure is here in kilogram force per centimeter square. So, on y axis scale is not normal scale, rather on y axis the scale you have is a logarithmic scale. So, while using this chart we need to be careful. First you select the width of footing and you can select the corresponding n values. So, n are varying from 5, 10, 15 and 20, 25, 30, and then our last value is 60. So, depending on the n values and the width b, we select the coordinate and then corresponding you find the value of settlement in meter, and this settlement you get is for a pressure 1 kilogram force per centimeter square. If your pressure is high, let us say 2 kilogram force, then you multiply by 2 and get the answer from this. So, this is how this chart is used, and in this chart there is one correction which is called the correction for water is applied, and this correction factor for water is given in this figure also. And if your water table is at a depth below b from the base of the footing, and in that case no correction need to be applied for the settlement. This is the same as we discussed for the shallow foundation bearing capacity while discussing IS code. So, if you have this correction factor, if it is more than b, no, it is not to applied. But if your water table is between the base of the footing and a width b, then the correction factor is applied like using this relation, where dw dash is the depth of water table from the base of the footing. So, if this depth dw dash is 0, then correction factor will be 0.5. However, if dw dash equal to b, then correction factor will be 1, that means no correction need to be applied. So, using this correction factor, this will, as a naturally when water table is present, the settlement is going to increase, it is not going to decrease. So, this correction factor actually whatever settlement you get from this chart, then you divide that settlement using this correction factor, not multiply by this correction factor. So, for the settlement, correction is applied reverse way what we do for bearing capacity. So, in general the presence of the water will decrease your bearing capacity while it is going to increase the settlement, that is the concept. So, once the correction factor is found, then you divide the value of the settlement obtained from this chart and get the corrected value of the settlement. So, this was the case here, and this is we have already discussed, and this Cn the correction applied after this chart. Now, continue with that. What you have here, once correction is applied, then this was related to standard penetration test. Now, another way is CPT, that is what we call cone penetration test, CPT. And using CPT, settlement of each layer is found out, and then you add the settlement of each layer to find the total settlement. Settlement of a particular layer. So, what we do using CPT, in case of CPT, you divide your stratum into a number of layers, layer 1, layer 2, layer 3, layer 4, and then you have for different layers you obtained what is called QC. QC is called here, which is given here, in these relations are also coming. So, the QC is nothing but the QC is called cone penetration resistance, cone penetration resistance, that is the value which we find from CPT. And once this QC is known, then using these two, either of these two empirical relations, one is given by De Beer and Metras and another by Mehrov, one can find the value of compressibility coefficient C, where it is in this case QC divided by sigma 0, and sigma 0 naught is effective overburden pressure at a particular depth for which you want to find the settlement. So, once C is known in this equation, H is the thickness of the layer, sigma naught bar is the effective at the depth of which test need to be carried out, and this delta sigma is increase in vertical stress at the middle of the layer due to this loading. So, once we put all the values here, then we calculate the value of settlement in this case, and once settlement S for this layer, one layer is known, then we calculate for layer 2, layer 3, layer 4 and add all the settlements to get the total settlement, and using what we call the CPT method or cone penetration method. Then continue with that. So, we have settlement of foundation on granular soils. Now, let us discuss the third part of the settlement, which is called modes or types of settlements. That means we discuss in detail total settlement, but it is not only total settlement, or total settlement is normally that settlement which is consist of all the parts. But when we talk about types, then it could be in three parts. One is called uniform settlement. For the uniform settlement, your buildings settled uniformly. So, which is the case here in A case. If you see the A case, then you see the solid line was a position before the settlement, and the dotted line is the position after the settlements. So, the base of the building was initially here, and this moved down to by a distance S downwards. So, S is the uniform settlement in this case, but when you have a number of buildings, both the buildings may not settle by the same amount, which is the case in the case of what is called in differential settlement. So, you have this one building and then you have the another building here. So, in this case, the footing of first building settled by a amount n S1, while footing for another case identical, it is exactly identical, but it is situated at a center to center distance of L. The distance between two footings center to center is capital L. The first one settled by an amount S1, while the second one settled by an amount S2, which is quite high compared to S1. So, the difference between these two S2 and S1, that is S2 minus S1, is called differential settlement. So, this is normally represented by delta. So, delta is nothing but S2 minus S1, and if you divide this differential settlement by the length L, then this ratio is called angular distortion. The third quantity is called the tilt. When we have the tilt, if one corner of the building settled less and another corner settled more, that means between two edges of the building there will be differential settlement, which is shown in this figure C. So, this corner left corner settled by amount n S1, while right corner settled by S2, which is quite higher compared to S1. Again, the difference S2 minus S1 is the differential settlement, divided by the length gives you the tilt. So, tilt in this case, though formula is same, here it was angular distortion, here it was called tilt. So, building get tilted by an amount given by delta by L. So, this can be find out. So, obviously, that we want that the building there could be uniform settlement rather than the differential settlement. So, the building can settle uniformly. So, we try to avoid the differential settlement. Now, continue with this, there are like that some researchers have given relation between total and differential settlement, because it is difficult to have the total differential settlement to get. So, what is done, this for example, one of the researchers Bejiram, they have worked. First of all, in no case the differential settlement will be more than total settlement. So, normally it is expected that maximum differential settlement for the granular soils can be at the most 75% of the total settlement, and in clay soil the difference is much less than the total settlement, and normally differential settlement, because in the clay you have more uniform settlement. So, as a result, normally differential settlement does not exceed more than 50% of the total settlement. Bejiram's research in 1963 has observed the settlement characteristic of structures on sand as well as clay. So, if you see in this figure, the first A and B part, that is for the sands, and the another A and B are for the clay. If you see that there are relation, the first A part gives you the relation between angular distortion versus maximum differential settlement, B between maximum differential settlement versus maximum settlement. So, how we can utilize these charts? So, if you have fixed up from the codal values and other things the maximum values of total settlement, then for using this maximum value of total settlement, using this chart we can calculate maximum differential settlement. Once you know the maximum differential settlement in millimeter, then we can find the angular distortion using this. The same is the case for the clay, and if you compare the values, then you could see that maximum value of settlement for the here it is 120 mm for sand, while it is going up to 450 mm. Same is the difference for the differential settlement as well as the angular tilt. So, that means the value of the settlement could be higher than the value of settlement could be higher, or allowable settlement could be higher for the clay compared to for the sand, and the simple reason being that for the clay we expect that settlement will be more uniform rather than differential settlements. So, in case of clay more settlements can be permitted than compared to sand. Continue with that. Now, the last part of this settlement, that is the limiting angular displacements, and this limiting angular displacement depends on type of buildings and other issues. So, this table gives you the type of structure problems. Angular distortions is denoted by delta by L, where delta, as we already discussed, it is differential settlement, and L is the length for this structure, or it is the center to center distance between two footings. So, this ratio delta by L, when difficulties with machinery sensitive to settlement, it should be 1 by 750. For dangers for frames with diagonals, 1 by 600. You want to put the limit for buildings where cracking is not permissible, then it should be 1 by 500. Limit where first cracking in panel wall is to be expected or difficulties, then it is 1 by 300, and limit where tilting of high risk building may become noticeable, 1 by 250, and then finally, if you have the considerable cracking in panel and brick walls, then safe limit is given is last is 150. So, as you go from down to up, then the angular distortion is increasing, or when you come from top to bottom of this table, then this is decreasing, because and accordingly the severity of the problem is increasing from top to bottom. So, thank you very much for, so this complete the settlement part, and in the next lecture we will talk about that some numerical examples on bearing capacity as well as the settlement. Thank you for your kind attention and patience.